introduction, and thank you everyone for having me here. In the past 2 days, I've had the pleasure of talking to many of you and learning about the wide range of science that's being done here at UT Austin. And through my talk today, I hope to showcase to you some of my work in earthquake and volcano mechanics. And then towards the end of my talk, I will also give you an overview of my vision for future research. So the subject of my talk today is Caldera collapse earthquakes. Perhaps it comes as a slight surprise to many of you that Caldera collapse should be associated with earthquakes. The fact that the imagery often we conjure up is these explosive eruptions and pyroclastic flows associated with silicic volcanoes. But in fact, a defining feature at basaltic volcanoes for this Caldera collapse are episodic earthquakes. So shown here on the upper right-hand side is a time-lapse video of Kilauea volcano summit in 2018. What you're looking at is 62 magnitude 5 earthquakes, each of which is a 5 to 10 meter downward slip on the fault. And for me, this is one of the most interesting mechanics problems in geohazards, really combining the physics of seismic waves and magmatic flows and frictions on the fault. And up until very recently, it has been challenging to understand the detailed dynamics of these earthquakes, partly because of this interaction between the earthquake and the underlying magma reservoir. And one of my contributions in this field is to develop the first self-consistent model incorporating the nucleation of earthquake, its propagation, and the subsequent collapse and its interaction with the underlying reservoir. That's really a trilogy of waves, magma, and friction. But before we go into the details of this story, I want to just briefly motivate for why we want to study basaltic Caldera collapse earthquakes. So I think arguably, from a societal perspective, silicic eruptions are much more consequential given the potential hazard to our society. And volcanologists, by studying the morphology, the geochemistry of the eruption deposits, as well as the plutonic rocks, they can deduce insight into the state of the reservoir during eruptions. For example, some of the great work's being done here at UT Austin. But very little is known regarding the very short dynamics of these eruptions at a timescale of seconds to minutes. And one of the questions that fascinates me is whether large earthquakes accompany these eruptions. And if they do, what is the role of earthquakes in influencing the eruption dynamics? Although there's very scant seismic observations of silicic caldera-forming eruptions, there is some in the literature. And if you look carefully, there's evidence for large earthquakes during silicic caldera-forming eruptions. Shown here is an excerpt from our paper about Wang 1912 caldera-forming eruption in Alaska. And it shows that of the more than 50 earthquakes detected, some of them are as large as magnitude 6 and 7. So I would say there's strong evidence that at least earthquakes accompany some of these eruptions. The question remains, what's the role of earthquakes in influencing the eruption dynamics? And I would argue that basaltic Caldera collapse earthquakes is a very good starting point for starting to understand the interaction between earthquakes and magma reservoirs. So here I removed the explosive eruption pyroclastic flow from the image. I want to emphasize at basaltic volcanoes, the eruption really is directed to the rift zone of the volcano. So it's not erupted through the rainfall system like in silicic, more explosive eruptions. And there's a few features here that makes basaltic Caldera collapse earthquake an ideal starting place. In terms of the waves, the basaltic volcanoes tend to be better instrumented often because it's relatively low explosivity. So with this seismic instrumentation, we can learn a lot about the dynamics of the earthquake. And if we want to understand earthquake, we need to understand friction on the fault. And basaltic Caldera collapse just removed some complications in terms of having turbulent eruption coming through the ring fault. And in the same vein, for the magma component, the reservoir is, for basaltic volcanoes is comparatively crystal poor. And this also makes it ideal starting point for starting to understand the interaction between the earthquake and fluid. And the most important reason, of course, is that we see basaltic caldera collapse eruptions much more often. In the past 2 decades, we've seen it in Miyakojima in Japan in 2000, in Piton de la Fournaise in 2007, in Baden-Volga in Iceland in 2013, and Kilauea in 2018. We'll be mostly looking at the Kilauea eruption in 2018, the one that's sort of near and dear to my heart, since I spent much of my PhD studying it. So we're looking at the big island of Hawaii, and specifically zooming into the southeastern corner of the island. And there's 2 geographic locations, the summit of Kilauea volcano, and then 40 kilometers to the east in the rift zone where the eruption occurred. Over the course of 3 months in 2018, there was near continuous eruption in the rift zone. And this is accompanied by the collapse of the summit in 62 magnitude 5 earthquakes. After the eruption, the summit landscape changed dramatically. There was a crater that formed as a result of the collapse. That's 500 meters deep, and that's equivalent to 5 of the UT towers on top of each other, just for reference. And the erupted magma covered an area that's more than 20 times the size of the UT main campus. And it was among the costliest in US history in terms of the economic loss and damage to infrastructure. So why did the eruption result in so much magma being erupted? One thing that we have learned through studying of this basaltic caldera collapse is the fact that earthquakes sustain the eruption. And this is a point that has been reaffirmed at Kilauea with abundance of geophysical data. So in this cross-sectional view, we see that the caldera block is supported by the pressure in the magma reservoir from below, as well as the shear stress on the fault from the side. So in between these caldera collapse earthquakes, which is a period of 1 to 2 days, we know the pressure in the reservoir is decreasing exponentially. And that is because we have GPS stations outside of the ring fault showing this kind of exponential decay in deformation. And correspondingly, with the pressure decrease, the shear stress has to increase on the fault, sort of from a static force balance kind of view. And at some point, the shear stress reaches a critical value. An earthquake would nucleate on the fault and rupture the entire fault, allowing for the block to collapsing into the magma reservoir. And at this point, we see an instantaneous pressurization of the reservoir. So taken together, we can see the time series for deformation outside have these sawtooth shapes. And for the deformation on top of the caldera block, we see this downward step. Each downward step is a collapsed earthquake. So what we'll see is a trilogy of waves, magma, and friction. We'll learn that seismic waves not only encode the dynamics of the collapsed earthquakes, but also modulate the dynamics by carrying momentum. We'll see that caldera collapse earthquake is not the only type of slip behavior on the fault. In fact, we'll learn that the fault friction is spatially heterogeneous on the fault, and that's integral to explaining a lot of the seismic observations. We'll learn that the physical properties of magma, such as viscosity, have a strong influence on the magnitude of these earthquakes. So first, let's look at seismic waves. On the right-hand side is the summit topography of Kilauea volcano. So each of these lines roughly correspond to where a fault exists. The innermost fault line here is where the ring fault is. And these 4 points is where the 4 of the caldera collapse earthquakes are nucleated from. And the waveform on the left-hand side are vertical velocity waveforms recorded at an accelerometer that's only a few hundred meters away from the fault. The first thing we'll notice in these seismic waveforms is a lack of high-frequency content compared to tectonic earthquakes. And this is, in fact, due to the fact that this earthquake's duration is controlled by the volume and compressibility of the reservoir. It's now controlled by the fault's dimension and the rupture speed, like on tectonic earthquakes. So the dominant period here is about 2 seconds. Second thing we'll notice is the consistency among these different earthquakes. And this immediately tells us there's a universal mechanism behind these earthquakes that we can learn by interpreting the waveforms. To interpret the waveforms, we'll perform simulations, and to perform simulations, we'll make assumptions. And assumptions are good reference points by which we start to learn something new about Earth. The first assumption we'll make here is that at Kilauea volcano, the sub-Caldera magma reservoir has a melt-dominated region. And this is indicated by past geochemistry studies showing that the input and output of magma from the system have very highly correlated temporal trends, which requires a melt-dominated region. And from geodesy, such as shown here on the upper right-hand side, we can constrain the volume and geometry of the reservoir as well as its location. The reservoir is roughly 2 kilometers in centroid depth, 4 cubic kilometers in volume, and geodetically, you can model it as a spheroid. We assume here the ring fault is just a cylindrical shape. This is for no better reason than we want to understand the more universal mechanisms behind these earthquakes, not to learn anything specific to the geometry of the fault. And we know the fault dip is close to being vertical by modeling the deformation outside the ring fault as a function of radial distance. And we'll assume that during each of these earthquakes, which lasts about 5 to 10 seconds, mass is being conserved in the reservoir. It's a fair assumption for such a short duration of time. And last assumption is that for basaltic magma, due to its relatively low viscosity, we'll model it as a so-called acoustic fluid, which just means that the fluid has no viscosity and does not allow for the propagation of shear waves. Some of these assumptions will come back to reevaluate that. Just a quick note on the setup of the simulation. So the simulation is done in Seislaw. It's an open source finite element code for dynamic rupture simulation, and some of you here are familiar with this code. And the model domain is really just a rectangular domain, so the waves being absorbed at the boundary, and earthquake nucleates on a cylindrical fault, and underlying that is a somewhat spheroidal reservoir. This is based on geodetic modeling. Here I'll walk you through 3 stages of the Caldera collapse earthquakes that we identify in the simulation. Later we'll use the intuition we develop here to try to understand the seismic observations. The first and second row here shows you the vertical particle velocity. Red is moving up and blue is moving down, and it's in map and cross-sectional view. The third row is a cross-sectional view of pressure change in the reservoir and mean stress change in the surrounding crust. Stage 1, earthquake is nucleated on the northwestern side of the ring fault, and then it propagates bilaterally around this cylindrical fault. This instantaneously initiates a downward traveling pressure wave in the reservoir. Remember, we modeled it as shear wave cannot propagate through. So this pressure wave will continue to travel downwards. At about 4.5 seconds, it reaches the bottom of the reservoir. At this point, the reservoir starts to pressurize almost uniformly. And this applies an upward force on the downward traveling Caldera block and starts to decelerate it. At about 7.2 seconds, the Caldera block has reached a static equilibrium again because of the increase in pressure in the reservoir, and the fault slip has ended. And what we're seeing here in terms of the surface deformation is mostly a resonant motion due to waves being trapped in the seismic reservoir. For the seismologists in the audience, oftentimes we think in terms of seismic representations of an earthquake instead of these finite sources. And it's very useful here to interpret the simulated waveforms in the near field at a point A that's a couple hundred meters away from the fault. The first stage, when the rupture initiates, we can think of it locally as almost a double couple because it's rupturing such a small area on the fault. But as the rupture propagates around the fault, it's mathematically equivalent to integrating these double couples at different azimuths. So what you're left with is upward force on the crust and downward force on the magma. But for a receiver outside on the ring fault, at this point you wouldn't see the effect of the downward force because it has not yet reached the bottom of the reservoir through pressure waves. So if we look at displacement, it's radially outward and vertically upward for stage 1. For stage 2, the pressure waves reach the bottom of the reservoir. This applies a downward force on the crust, and so we see a radially inward and downward displacement. At stage 3, the reservoir has pressurized uniformly, and this is equivalent to expansion moment. So we see a permanent radially outward and upward displacement. On top of that, we see these small wiggles. These are the resonance effects. So each of these features can in fact be identified in the observation. So on the left-hand side, again, I show the topography of Kilauea Summit. The red circle is approximately where we put this cylindrical ring fault relative to a accelerometer, UWE. So it's a few hundred meters away. Each of these points here indicates the hypocenter of a Caldera collapse earthquake. Comparing the waveforms shown on the right-hand side, the black one corresponds to an earthquake that nucleated on the southwestern corner of the ring fault, and the gray one corresponds to an earthquake that nucleated on the southeastern, sorry, did I say it twice? Southwestern and southeastern part of the fault. And then the red one is a simulation. You can see we can identify, for example, where the displacement starts to ramp up is where the dynamic rupture starts. Where the first big downward motion starts, this is where the pressure wave has reached the bottom of the reservoir, applying a downward force on the crust. And we can see this later resonant motion, which is still a little bit less clear in the observation. And we oftentimes in seismology compare velocity waveforms. So on the right-hand side, these black lines are the observation, and the red lines are the simulations. So we can see they roughly match phase by phase. So I want to emphasize how remarkable it is, given all of these assumptions we've made about the Earth. The strongest assumption here is the fact that a magma reservoir is comprised of a melt-dominated region, and yet we can explain the observations. At Kilauea, this melt-dominated model is not the only kind of model for the magma reservoir. For example, it has been suggested that these reservoirs are really a plexus of silts and dikes. In those models, melt is really residing in these very thin layers surrounded by sort of poroelastic medium. That kind of model, however, is inconsistent with observation and the simulation here for two reasons. One is that at the time scale of the earthquake, which is 5 to 10 seconds, that kind of plexus of silt and dike model will effectively behave elastically, and it will generate a lot of high-frequency seismic radiation, which we don't see in the data. And the second reason is the duration of the earthquake, as I mentioned, scales with the compressibility of the reservoir. If it's in fact poroelastic medium with silt and dikes, it's very stiff, and the duration of the earthquake would be probably less than 10% of what we see here. So it's remarkable that our understanding of the reservoir perhaps is not too far off from the reality. But we do modeling not to match the data, but to learn something new about the Earth. And in fact, if we look at all the earthquakes that nucleate on the northwestern side of the fault, we'll notice this feature in the waveform that precedes the dynamic rupture. Our interpretation of this phase is that it's a complex nucleation phase, meaning that when earthquakes grow, initially they're small, and they're very sensitive to the surrounding stress. And for a fault like this, it's got quite irregular shapes to it on some corners. And it's possible that on the northwestern side, it has a stress condition that's not very favorable for the growth of the earthquake. So what's happening here is the earthquake attempted to dynamically rupture, it slowed down, and then attempted a couple more times before it was finally able to rupture the entire fault. And for understanding why and when these earthquakes occur, these kind of features are essential for our understanding. But we would not have noticed this kind of feature had we not known the more universal dynamics behind these earthquakes, which is the intuition brought to us through these simulations. I want to make a quick side note that numerical simulations are very powerful, but they can be expensive. So each of these simulations takes about 115,000 CPU hours. I probably ran more than 100 of these simulations throughout the course of writing this paper. And that's equivalent to about $2,000 in electricity alone, and have a carbon footprint of about 5 round trips from LA to Austin. My personal preference oftentimes is to start with pen and paper analyses, which I think a lot of times reveals as much about dynamics, and at least tells us under what kind of scenarios we can sort of make a shortcut. So a case in point is seismic wave radiation from the side of the ring fault, which is illustrated in the simulation here. So if we want to understand, for example, just how much slip is occurring on the fault per earthquake, it's very hard to analytically solve for it accurately because of potential wave radiation from the fault. In fact, if the fault is a planar fault, we know how to make approximations for the effect of wave-mediated stress, but not on these kind of circular cylindrical shapes. So we did a kind of a very simple model problem. We have a cylindrical fault. The block in the middle can move in another page, and it's infinite in another page. And we allow the material to be different across the fault in terms of shear modulus. And essentially, you solve the wave equation in frequency domain and look for the relationship between stress change, wave-mediated stress change, and the imposed slip. And we discover there are limits in which we can analytically solve for the solution. One limit is when the wavelength is much longer than a ring fault. And intuitively, in that case, the motion inside the Caldera block is uniform. So it's just like an inertial mass. So we can analytically solve for the displacement in this case. Another limit, when the wavelength becomes much smaller than the ring fault, the wave-mediated stress becomes important, and yet there's another limit where you can solve for things analytically. That's when the shear modulus in the ring fault is much larger than the outside. But beyond that, resonances becomes important, and you have to numerically solve for the problem. Next, I want to switch gear a little bit and talk about the effect of magma viscoelasticity. So far, we have assumed that the basaltic magma can be modeled as acoustic fluid, which is a fair assumption given our specific problem, but it may not be the right assumption in all scenarios. Magma, as we know, are viscoelastic, and one of the simplest models for viscoelasticity is a Maxwell rheology. And schematically, the idea is you take a spring which is elastic and a dashpot which has a viscous flow to it, and add them together, concatenate them together in series. If you deform it very quickly, stress develops in the spring, but then it will be relaxed over time due to the flow in the dashpot. And an important concept here is relaxation time, which is the viscosity divided by the shear modulus. To investigate the effect of magma viscoelasticity, we again come back to SISO. But the problem here is that, unfortunately to us, SISO is not really designed to model any fluid flow. But fortunately, it has a feature called generalized Maxwell bodies, which is used for modeling attenuation of seismic waves. The idea of generalized Maxwell bodies is to take these spring and dashpot units and put them in parallel with each other. By adding more and more and more of these units, eventually you can approximate any kind of rheology, at least theoretically. And so what we did here is to devise an inverse workflow to tune the SISO input such that we can emulate a specific rheology. And here I want to say that we look at a very simple geometry. This is just a cylindrical magma reservoir, even less realistic. And we just want to focus on the effect of viscoelasticity. So here's an example for a Maxwell rheology magma that has a viscosity of silicic magma, 10 to the 8 Pascal second. What we're looking at here in this animation, on the left-hand side is mostly motion in the crust. On the right-hand side is the motion in the fluid in the reservoir. These arrows are indicating a downward motion. The downward motion of magma is initiated by the Caldera collapse itself. And a key feature here is that the velocity decreases parabolically towards the chamber wall. This is a defining feature of a boundary layer developing in the fluid. And the boundary layer is essentially because you have either an elastic or some kind of rigid surface, and the fluid flowing over it have to have a no slip condition, so the velocity decreases towards the wall. And what the boundary layer does in these dynamics is to diffuse the vertical momentum in the magma and in the Caldera block laterally into the crust. The thicker the boundary layer is compared to the dimension of the reservoir, the more of that momentum is diffused out, and so eventually it impacts the magnitude of earthquake. Here I show the time dependence of subsidence of a caldera block in black line, and in dotted line the pressure change in the reservoir. So you see for basaltic caldera collapse, as you would expect, subsidence occurs, pretty much and it decelerates, and then it goes flat. And correspondingly, due to volume reduction, the pressure goes up and plateaus. Compare that with silicic magma, in this case modeled as Maxwell rheology, we see a reduction in the displacement as well as pressurization. So just as a mental exercise, if you were to just replace the basaltic magma with the silicic magma, and ignoring how the eruption style might change, we can try to model the amount of magma erupted over different cycles, collapse cycles. And over a mere 4 cycles, the basaltic magma would have erupted 20% more due to more pressurization per earthquake. So this is just to emphasize the importance of viscosity in this case. Another aspect I want to talk about is the periods in between the earthquakes. So each of these vertical lines here shows you the timing of a caldera collapse earthquake, magnitude 5 earthquakes. And in between the earthquakes, we refer to it as interseismic or intercollapse. These periods are extremely important to be understood because stress and strain builds on the fault in between these earthquakes. And at Kilauea, there are tens of thousands of small earthquakes being detected in between the earthquakes. And I show here in map and cross-sectional view of this microseismicity. And what's peculiar about this microseismicity is their time dependence, plotted in these blue lines here. So this is the cumulative number of microseismicity in between these large magnitude 5 earthquakes. What we're seeing is that after each collapse earthquake, the rate of cumulative seismicity starts to increase. It accelerates, and eventually it goes to a constant slope, which means the seismicity rate has reached almost a steady state. This is peculiar because it's very different from foreshock, aftershock sequences on tectonic faults. So here is a typical aftershock sequence on tectonic fault. We see the seismicity rate decreases, in fact, as the inverse of time. And so it's puzzling. What could potentially explain this? Our hypothesis is that the fault creep drives this seismicity. We have GPS station on top of the caldera block and outside on the ring fault. So by differencing the displacement there, we can know the relative motion on the fault. And here plotted is the fault creep in between the collapse earthquakes, color-coded by different intercollapse periods. We see they all have the same time dependence. They accelerate into a steady state, very similar to the cumulative microseismicity. In fact, if you plot them against each other, you see an almost linear correlation between the two. This strongly suggests that seismicity is driven by fault creep. But this does not answer why this fault creep is occurring in the first place and what explains its time dependence of the fault creep. This kind of meter per day kind of fault creep, as far as we know, is the fastest ever observed on a natural fault. To model that, I need to first introduce the idea of rate and state friction. The idea of rate and state friction was first developed in the laboratory settings in the 60s and 70s. The idea is you take polished rock surfaces, you put them against each other, and you start to drive relative motion between the two at a constant rate. In doing so, you try to suppress any instabilities for the development of earthquakes. And at some point, you instantaneously increase the slip velocity, and what you observe is that friction increases at this point, and it increases by a magnitude proportional to the log of the final velocity divided by the initial velocity times a constant a, which is called the rate and state direct effect parameter. As the blocks continue to slide past each other, the friction decreases to a steady state. And if it decreases to a level that's above the original friction, it's called velocity strengthening. And if it decreases below its original value, it's called velocity weakening. Broadly speaking, velocity weakening friction allows for the development of earthquake, and velocity strengthening frictions suppresses instabilities and promote aseismic slip and fault creep. So we'll test whether velocity strengthening in this case can explain the observed fault creep. On tectonic faults, fault motion is driven by far-field plate movement. At calderas, the motion on the fault is ultimately driven by the pressure change in the underlying reservoir. And to describe the fault motion, we have a very simple momentum balance equation. On the left-hand side, the first term is initial stress, initial shear stress on the fault. And this is eddy stress that's left behind from previous earthquakes. And the second term is the so-called loading term. This is what builds up the stress. And we know the pressure in between the earthquakes is decreasing exponentially from GPS. And to keep a static balance on the caldera blocks, the shear stress must increase like a 1 minus exponential. At least we know the time dependence here. On the right-hand side is the frictional resistance. And it's a product of effective normal stress multiplied by a latent state friction. So it depends on the slip rate as well as slip history. Specifically here is a velocity strengthening friction. And for steady state velocity strengthening friction, we can analytically solve for the time dependence of fault creep as a function of time. And it comes out in this form. That is the right form for the observation. It has a steady state slip rate, which has complex dependence on latent state parameters, but nevertheless a constant that you can directly infer from GPS measured creep. And the free parameter called a dimensionless stress parameter, alpha. And this parameter depends on the magnitude of shear stress change in between the earthquake, as well as the latent state parameters. So we can choose the parameters that are relevant for basaltic wall rock on the ring fault. So each of these gray lines here is fault creep as a function of time. And we show that for the appropriate range of alpha, we can explain the observed range of fault creep, and they all have the right time dependence. What we have learned is the following. So for this microseismicity to occur on the ring fault, we must have velocity weakening patches on the fault, and these are called asperities. The reason there's so much seismicity going on in between the earthquake is because most of the fault is creeping. It's moving aseismically, and yet there are points being stuck at these asperities. And to explain both of these observations in between the caldera collapse earthquakes, we really need spatially heterogeneous friction on the ring fault. And just anecdotally, in 2022, I was with some USGS folks at the caldera floor, and I took this photo towards the southwestern side of the ring fault. And we see this hydrosomally altered mineral on the ring fault. And these tends to be having a lot of phyllosilicates in it, and in laboratory settings tend to be very, very velocity strengthening. So perhaps the hypothesis is not too wild, I guess, given that we do see this kind of material on the fault. So what we have learned is the following: that the seismic waves not only encode the dynamics of the caldera collapse earthquakes, but also modulate the dynamics by carrying momentum. And the physical properties of magma, like viscosity, can significantly influence the magnitude of caldera collapse earthquakes. Spatially heterogeneous velocity weakening and strengthening friction on the fault is required to explain the diverse range of slip behavior that we see. And if there's one take-home message, it is that caldera collapse eruptions are sustained by earthquakes. And perhaps one day we will be able to better model silicic eruptions and understand the role of earthquakes in controlling the dynamics. Next, I want to switch gear again and talk a little bit about my other work. So after the 2018 caldera collapse, as you can imagine, about more than 1 cubic kilometers of magma were erupted. So it causes large imbalances in pressure in the different magma storage regions at Kilauea. And there were these large deformation patterns on the surface measured by INSAR and GPS. And these are time-dependent deformation. So we utilize this historic data set and building a very simple physics-based model describing how magma is being transferred between the different magma reservoirs. And we were able to, for the first time, estimate the system-wide hydraulic connectivity between the different magma reservoirs. And working on that project made me start to think about how we model the surface deformation related to complex magma reservoir geometries. currently, for very simple geometries, we simply go with analytical solutions. But ultimately, in many cases, those models are not sufficient. And numerical methods can be expensive if you have to run these simulations for tens of thousands of times for inversion. So one idea is to build these surrogate models for modeling deformation using neural networks. In this specific case, because of the problem at hand in terms of these complex geometries of reservoir, graph is a perfect tool to represent these geometries, given how variable the surface shape can be. So what we did here is to decompose any geometry with spherical harmonics. And in the inversion, when you go from surface deformation to the geometry of the reservoir, you can then try to constrain the uncertainty on each mode of spherical harmonics. And now you will have a range of different shapes that potentially correspond to your surface deformation, allow you to better propagate uncertainty from data to the parameter space. The third example is I also have interest in modeling aseismic and seismic slips in enhanced geothermal systems. This is a case in Cooper Basin in Australia, where they injected fluid into a pre-existing fault zone for about 12 days. And in this case, it was, again, very fantastic data in terms of injection rate history as well as wellhead pressure history. And most importantly, a very nice seismic catalog that shows almost a cloud of seismicity propagating on the fault. So we built a hydromechanical model. So this has a rate state friction on a 3D fault. There's velocity strengthening. And in the surrounding, there's a cloud of velocity weakening patches that can generate microseismicity. And you drive it with injection fluid. And we show that you can hindcast the observed seismicity, as well as to show that this seismicity initially are driven by the weakening of the fault by the pressure, but later on by aseismic slip on the fault. My vision for future work is to combine analytical theory, numerical modeling, and machine learning tools to understand the mechanics of earthquakes and volcanoes, and crucially to enable geophysical monitoring of the relevant dynamics. And I will show three short examples of that. The first thing I'm interested in is in exploring the interaction between fluid and non-planar faults, specifically the so-called rough faults, in the sense that faults are fractal in geometry, and when you have slip accumulating on faults that are non-planar, you have an undulating normal stress perturbation. And this will correspond to permeability structures for the fluids that are also variable as a function of space. And so we can try to understand quantitatively how does fluid flow correspond to the different styles of seismicity and the spatial temporal dependence of the earthquakes. Another aspect is thinking about this fluid not as a problem of diffusion, but when you have viscous fluid being stuck in between the fault planes. So think about the fault as a conduit for fluid. When you have geometrically rough faults during the earthquake, the mismatch on the two sides of the fault will pressurize the fluid and potentially cause a little bit of opening motion on the fault. And that will be relevant for understanding, for example, how melt is generated in between, on these earthquakes, or how magma propagates through potentially pre-existing weak zones in the crust. And I think there's applications beyond earthquakes. For example, at glaciers. Glaciers move on the bedrock, and it has been shown that by some of the great work done here, that the pressure change at the glacier bedrock interface correspond to the slip rate or the overall motion of the glacier. So by doing a little bit of tweak to our modeling for earthquakes, we can also potentially simulate this kind of phenomenon. The second direction I'm interested in exploring is the application of machine learning for mechanics problems in geoscience. One example of which is earthquake sequence simulations. So far, a lot of times earthquake sequence simulations are used for understand the fundamental mechanics of faults, but not so much in forecasting of future behavior. And part of the reason is that it's really hard to balance the complexity of the model and the computational cost. And one way we can approach this is to take one of the most efficient numerical methods out there, which is called boundary element, and enable it to do more complex things. The reason the boundary element methods are efficient is that you're parameterizing a 2D surface, not a 3D volume. But that's also its limitation, in that we cannot represent 3D elastic structures, in particular time-dependent elastic structures. And so we can replace the elastic interaction on different parts of the fault with a machine learning emulator, such that we can generalize to more complex elastic structures that potentially evolve over time. For example, in the case of fault damage zone. A third direction of interest is in connecting numerical simulations with seismic observables. Oftentimes, for complex source processes like Caldera collapse, we have these numerical simulations that produce very complex behavior. But from the perspective of seismology, oftentimes we only have observation from very far away, effectively making the source a point source. In those cases, we can resolve still the temporal dependence of the source in terms of force, moment, and torque, but it's very hard to constrain these finite processes. So the link in between the numerical simulation and the seismic observation is a representation theorem, which essentially is a bookkeeping tool. Here, in collaboration with Eric Dunham, I developed this seismic representation theorem that allows you to write point, force, moment, and torque in terms of displacement and stress so that you can derive from numerical simulations. So now you perform the numerical simulation, you take those parameters that you can actually evaluate, put in the expressions, you have a physically self-consistent representation of the source. And one example of that is when we apply this to the simulation of silicic Caldera collapse. And we see this silicic magma rotating in the reservoir and applying tractions on the surrounding walls. And in fact, you can deduce a time-dependent torque from that process. What I think will be really interesting is apply this to source processes like landslides. There's a lot of interest in, for example, landslides in the Gulf of Mexico underwater that potentially have tsunami-genic potentials. And we can use this kind of pre-existing simulations of landslides to understand how the seismic observations correspond to different styles of landslides would be distinguished in seismic observations. And lastly, I just want to say I think it's a very exciting time to study mechanics problems in geohazards, given the advancements in numerical methods, in machine learning tools, as well as in the explosion of data from geophysics. And I want to say thank you again for having me here, and I will be happy to take any questions.